Okay, so thank you everyone for joining. Today we have Vijay Balasubramanian from Penn, who's going to talk about complexity and time evolution and all sorts of other stuff. So Vijay, thank you very much, and the floor is yours.
Great, thank you very much for this invitation. It's the first time I've given a virtual seminar, so it's going to be a learning experience for me. Anyway, so today I'll talk about the quantum complexity of time evolution. And this is work done with Matt DeCross and Arjun Kar, who are both students at Penn. And Arjun did a lot of the heavy lifting, and so did Matt. And Arjun's on the job market this year, so a job you should keep in mind. And Onkar Parikar also. Great, was a co-author of this. Great, so let's see. So let me start by introducing the notion of complexity, which I know some of you in this audience are already familiar with. So in many branches of physics, we talk a lot about complex systems. And what is a complex system? Well, typically it has many internal components. It's got many body interactions, multi-party correlations, and many sorts of emergent behaviors, which is why we think of it as complex. It isn't as simple as a sort of sodium chloride crystal. And so examples in other branches of physics include in biophysics, there's the dynamics within cells. There's the study of strongly interacting electronic materials where there's long-range correlations and entanglement between very many parties. There are social networks that people talk about these days, and even study in physics, complicated interactions between many parties on a graph. And in our field, we're typically interested in things like black holes and the microstates of black holes and the ADS-CFT giving rise to emergent space-times. And both of these, somehow, the last two, somehow that there is some sort of very, very complex microstate and or very, very complex interactions between many parties giving rise to various kinds of emergence. Now, the challenge here is to ask, at least if you think about things in that way, is to ask, what do you mean by complexity? What does that even exactly mean? And if you think about that, even in the context of black holes and ADS-CFT, you could ask, what is the difference between a simple system and a complex system? So, for example, since black holes are supposed to be chaotic and, the vacuum state in the ADS-CFT isn't chaotic, can complexity be used as, for example, an order parameter to separate integrable and chaotic theories? So there are many questions like this that we'd like to have the answer to, but it really hinges on having a definition of what complexity is. Of course, lately, in the ADS-CFT correspondence, there is the conjecture due to Susskind and collaborators that complexity may be somehow related to the volume or the action of the bulk space-time within ADS-CFT. But I would say that the challenge with that definition is, of course, we can all go off and calculate areas and volumes and actions and so on, and check for consistency of this idea. But the challenge is, well, you really need to know what complexity means in quantum field theory, in the dual conformal field theory, in order to really make progress in understanding this conjecture. So in view of that, it's useful to sort of go back and think a little bit about what people in computer science and information theory have called complexity, basically because in those fields, this is a term that has been given a definition and people have thought about for a long time. And in particular, I'm going to be interested in the part of the conjecture arising from ADS-CFT that maximally chaotic systems should have complexity growing linearly in time. This is, of course, a conjecture that comes about, but taking for granted the definition that complexity is volume or action or something like that, and then asking, how that changes in time. So we'll be interested to see if there's a useful definition of complexity in quantum field theory, which relates to this idea of chaotic systems showing this kind of linear growth. Okay, I can't see anybody's faces in this, so I'm going to ask, are there any questions? Or please just interrupt me and ask questions whenever you feel like it. Okay, great. So now...
We're good here in Potsdam. Please go ahead.
Okay. So here, oh, great. Here's page 2. So in computer science, the idea of quantifying complexity goes back to Kolmogorov, and at least in the 1960s. And Kolmogorov suggested that you could think about the complexity of an object by the length of the shortest computer program used to produce it. So you think of a Turing machine and a program, the Turing machine, that's supposed to produce the string of digits, that's the output that you desire, and you ask how big is that program, And by this definition, for example, totally random sequences are very complicated because there's no algorithm you can write down for it. And numbers like pi or square root of 3 are relatively simple. I mean, pi has a pseudo-random sequence of digits, but even that is simple because there's actually a simple algorithm, a procedure for generating all the digits of pi. So, and this idea that the complexity of a thing involves the shortest way of writing it, pervades even everything we're going to talk about. We talk about these days in physics regarding complexity. A variant of this idea, due to Rissanen, is the idea of stochastic complexity. So in stochastic complexity, you think of what you actually think about is you have some long sequence of letters or digits or whatever, a message basically, and you want to think about how to compress it. So you want to write this message out in the shortest possible, with the shortest possible code. And the complexity of the message is the size of the smallest code. And again, so what you think about here is you have this long sequence, and the sequence, in some sense has a deterministic component hidden within it that's easy. And then there's a random component which isn't easy. And so, well, the length of the message involves removing the deterministic component and again, compressing it to smallest size. And then, well, there you go. So in both of these definitions, it's the smallest description of the data. So the more modern version of this in computer science is that a complexity of a class of problems of size n, so something like that, is some f of n, where f of n is the size of the smallest program calculating the answer. So in computer science, this is an important distinction compared to physics. You always think about complexity in terms of a class of problems. So you think about the scaling of the difficulty with which, or the scaling of the smallest program to solve this class of problems. And the reason you do it that way is because, of course, different people may have different model computing machines, and really, and so you can't guarantee anything about the constants in this function. So you just try to guarantee the scaling, like it grows linearly with the size of the problem, or it grows quadratically or exponentially or whatever else, right? So it could be, so that's one way people think about the complexity of a problem class. And the version of this that we have been fond of lately in physics is the notion of circuit complexity, because somehow this feels like it matches well with the kind of sequence of quantum gates in a quantum circuit, where you start out with the zeros and ones, or for us spins at the bottom, and then you cascade a set of gates, and the set of gates eventually gives you an answer, and the answer f of n is supposed to be the size of the circuit required to complete the answer. Okay, so these are sort of traditional ways of thinking about complexity in other fields, which of course we're borrowing from in various ways. So for our purposes, we are interested in quantum field theory, or let's start with quantum mechanics, and we want to think about quantum mechanics as a computation. So we're going to think about the initial time surface, t equals 0 surface, where there's a state. And for concreteness, we're going to think about the state on a lattice with, let's say, a bunch of spins or something. Anyway, here's the state. And time evolution is a very particular computation. You take e to the minus iht, where h is the Hamiltonian. That's the unitary operator u, the time evolution operator. And that gives you some latent state psi of t. And in many recent developments, we're interested in asking how complex is the transformation implemented by this time evolution. So what do we want to say? What is the, intuitively, what is it we want to express? So consider this situation where, let's say, the initial state is some Gaussian bump or something like that. And let's suppose that after time evolution, it becomes a slightly spread out Gaussian bump like this. We might say that this is probably kind of a simple transformation. And it seems simple because, at least qualitatively, essentially small local changes to this wave function, to the initial wave function, will give the final wave function. So it seems like you can do some simple things. You can apply a few local transformations here and there and get this later state. By contrast, consider this scenario where you have some initial Gaussian lump, and the later function, wave function, is this hugely complicated, lots of bumps everywhere, and then it's entangled between this spot on the left and this spot on the right. It's entangled at short distances and long distances. That seems complex. And the reason it seems complex, at least qualitatively, is that it's going to require large local and global changes. and substantial non-local correlation and entanglement in order to produce the later state from the initial state. So what we seem to want, what we would like, is some sort of measure of this sort of complexity. And this being kind of simple would be satisfying, and this being kind of complex would be satisfying. And importantly, whatever this measure of complexity we come up with, we'd like it to have a relationship to other properties of interest in physical systems. So one way of saying this is, in math, the value of a definition is in its uses. So we define the notion of a compact set because sets that are compact satisfy many properties that are useful later in calculus. So in a similar way, whatever definition of complexity that we come up with should somehow relate to other things we care about or wanted to answer, or questions we wanted to answer in physics. So what could we do? Well, one way of thinking about things is to think about the complexity of states. So we think about this sort of state here versus this kind of very bumpy state, lots of correlations. And we could indeed try to come up with a definition of why the state here on the right is more complex than the state to the left. And we could come up with some useful definitions of that, and people definitely try to do that. An alternative, interesting thing to think about is not to think about this difference, because if you're just thinking about the complexity of states, we could ask, I have a machine that engineers the state on the right versus the state on the left, and why is one more complex than the other? But in our context, we're interested in what does physical time evolution do? So physical time evolution is a very particular computation. And so we're sort of interested in asking the question, if I have some initial state and becomes a later state, and the later state is complicated, well, it became complicated because of the physical time evolution. So, well, how complicated? What is the complexity of the physical time evolution? It's the actual computation that we are going to care about in the context of this talk. So we want the complexity, effectively, of the unitary operator u of t, which is e to the minus the Hamiltonian times time. Great. So, all right. So how would we go about coming up with a definition of that? So, all right. So to be concrete, we're here going to suppose that H is a discrete Hilbert space. So it's a Hilbert space of n over 2 qubits. At the end, in the discussion, we can talk a little bit about how to try to extend things to, continuum quantum field theories and so on. We should have a discussion about that. We haven't really completely dealt with that. And so here, the Hilbert space, is a product of n over 2 copies of the complex plane. And I'm going to drop the overall phase in the time evolution. And so from this point of view, I can consider the unitary group SU2 to the power n over 2. That's this ball over here. And the time evolution is going to be some trajectory, a very particular trajectory in this space. So at t equals 0, you're at the identity. Time evolution is a particular trajectory in the space, and we want to understand the complexity associated with that particular trajectory. If we're doing SU2, that's simply S3, so that's very easy. That's a sphere, and everything is known about spheres and so on. But really, the challenge here is that SUN is some complicated fiber bundle, and actually, the various trajectories and this, that, and the other are not known on that. And so. Right. So we'd like to understand the complexity of this U of this trajectory. So how would we do that? So, if you go back to the computer science idea of the complexity of things, you want to somehow relate complexity to the easiest or smallest or something, or most compact way of doing something. And so if you think about this, here's the time evolution trajectory. If I had of the time evolution operator. And so if I divided this up into discrete times like this, you might say that there's many infinitesimal little blocks of time. And you might say that the complexity in the language of computer science is the number of operations you have to do. So it's kind of sort of the number of steps you have to take, which is kind of sort of the length of this curve. You might take that to be related to the complexity of this time evolution. And so indeed, there is an idea going back to Nielsen, who works in quantum computation and information theory, that complexity should be related to the length of the shortest path between 2 points on this unitary manifold. In other words, it should be the length of the geodesic path. So in Nielsen's context, the way he was thinking was, well, you do a computation and you're over there, let's say, and in his language, there's a particular gate set you use to get to here. So what you do is you apply some gate, you jump from here to some point there, then you apply some other gate and you get to there, and you apply some other gate, and there's a particular gate set that you've defined to define the computation. So then what Nielsen did was that he talked about, on the one hand, this gate set that got you from one place to the other place, and the other hand, these geodesics, like G of t, on the unitary manifold. And he said, under some conditions, he proves that the geodesic length is a lower bound, upper bound. It's lower bound or upper bound? I think it's an upper bound on the number of gates you needed to use. So anyway, it provides a bound. But in our context, we don't have a particular gate set exactly in mind, and our time evolution is continuous in any case. So perhaps we should be taking the complexity of this unitary operator U of t as simply being the length of G of t. So we're just going to take that to be the definition in our continuum context, that the complexity is defined by the geodesic trajectory on this unitary manifold, basically that defines the fewest steps. We're just interested in asking if you wanted to get to U of t with the fewest number of steps possible, and we can do it continuously, there's not a specific gate set, then that's going to be defined as the complexity of this operator, right? So the next question is, so if you want to do that, of course, to get a geodesic and its length, we should decide what metric we should use. So that's the next thing to talk about. Okay, so how do we think about this? Well, suppose I have any operator O. So infinitesimally, I can think about that operator in terms of the Lie algebra, Vi times Ti. Vi are going to be the coefficients, and Ti are going to be the generators of Su n over 2. Actually, this should be Su 2 n over 2, I guess. Okay. So, and for our purposes, we're going to say that an operator is simple, a generator is simple, if it's k local, okay? So that means it's going to act on less than k elements. It's possible to modify this definition in different ways. We're going to be thinking about the SYK model, so this seems like an adequate definition. But if you had some continuum quantum field theory, you might take the definition of k local to mean not only that it acts on less than k elements, but that the k elements have to be near each other within some bounded region, or it's got a certain number of derivatives. You could come up with a definition of simple that seems reasonable for the theory at hand. And then we're going to have complex generators, which are everything that is not k local. Okay, so there's going to be the k local ones, which are simple, and the complex ones are not k local. So these ones, the simple ones, define the simple directions, if you like, in the tangent space of the unitary group manifold, and the not k-local ones define the complex ones. Okay, complex directions. And so the way we want to think about this then is that and this is again following the lead of Nielsen, is that the metric should be small in the k-local directions, and it should be large in the other directions. And we're going to take the large to mean e to the entropy, where entropy is a log in the dimension of the Hilbert space. And that's because Nielsen, from that early time, already we know that you need a large separation between these two to have a relationship, in that case, in the earlier quantum computation case, between the number of gates you need to do the computation and the length of the geodesic trajectory. So this kind of notion is going to try to capture the idea that an operation is complex if you have if you need to have the core, basically correlated action many elements. So again, the idea here is that an operation is simple if it's k-local, and it's complex if it's not k-local. So a unitary, whatever time evolution is produced by the unitary by U of t is going to be considered simple if you can do it by doing, if you can get to it by doing lots of things on local, on a small number of qubits at a time, and it's complex if you need to have correlated in a correlated way if you need to act on many elements at the same time, to produce highly non-local entanglements, this, that, and the other. Okay, so that's going to be the notion. Okay, so let's see. So given how time is passing, it's not entirely obvious I will get to the end. Actually, I may get to the end because I'm not getting any questions.
We started about 10 minutes late, so yeah.
Okay, I'll keep going. So from this perspective, we believe that complexity is the length of the shortest path between the identity and U of t. So it's the length of the geodesic, and so we're going to define complexity in quantum field theory and quantum mechanics in that way. We find the geodesic of the unitary group manifold, and we find its length in a metric of the kind that I just said. Okay. So, so because I may or may not get to the end, I'm just going to preview the results of the work, and then we'll take a brief pause and sort of take some questions, and then I'll continue with telling you how we arrived at these results. So we will show that three things. The first thing is, suppose you have the identity and U of t, which is the unitary time evolution operator, and then there is always a linear geodesic going with the identity and U of t of the following kind. Let's suppose that the Hamiltonian is built just out of simple generators, right? So T alpha are simple generators, so they're k-local with some coefficients. Then there's always a geodesic in the group manifold along that trajectory, and along the trajectory, you measure up the length, then the complexity grows linearly in time. The length, therefore the complexity, grows linearly in time. So you get T times the square root of something involving the coefficients in this Hamiltonian. So that's the kind of thing that one wanted for, let's say, maximally chaotic systems based on the holographic intuition. Next question is this geodesic minimal? So, right, you want to pick the shortest geodesics. So so we can guarantee two things: that this linear geodesic is minimal, and what's more, it remains minimal for a time that's exponential in size, e to the alpha s, where s is the entropy, up to some global obstructions, and that linear growth persists for an exponentially long time, again, as it should for chaotic systems, provided that the eigenstates of the system satisfy a particular property. And here's a property. You should reconstruct this kind of matrix Rmn. M and n are the different eigenstates of the theory. Now, alpha is going to index simple directions, namely k-local generators in SUN. And alpha dot here is going to index hard directions. So those are the not k-local, more than k-local. And so you construct this matrix, which is kind of an overlap between n and m when acted upon by the simple generators and then normalized in some way. Okay, so let's just first talk about what this quantity is. So this quantity tells you, in effect, how easy it is to move between one energy eigenstate, let's say n, and another energy eigenstate m through the action of simple generators, right? So if you make a simple, so you can imagine this in terms of a cold atom experiment. So, these guys who do cold atoms experiments, they'll make a gigantic, bench filling up a room with many qubits. And then there's the engineers on Hamiltonian, and the eigenstates N and M will be some very complicated configuration, correlated configuration, entangled configuration of all of these different spins. Now, then, if you say, well, please make the following operation on them, they can take all their lasers and sort of hit many qubits at the same time. So T alpha, so a simple operation is when let's say if your definition of simple is 2 local, then you can hit no more than 2 qubits at one time. And if you have many, and a complex operation involves hitting many more than 2 qubits, let's say. So the question is, can you go from one energy eigenstate to another energy eigenstate by essentially hitting the first energy eigenstate with something that touches 2 qubits, that kind of thing? And the statement, so this condition that this overlap, the ability to go from one energy eigenstate, another energy eigenstate, you can't go from one energy eigenstate to another energy eigenstate with simple operators. Is what we're trying to say here. In other words, RMN is will be exponentially suppressed in the entropy e to the minus 2s times some polynomial in s times some order 1 numbers. So suppose this condition is satisfied, then you can guarantee that this linear growth in complexity, because driven by this linear geodesic, persists for an exponentially long time, up to potential global obstructions, which we haven't been able to address fully. So we call this thing the Eigenstate Complexity Hypothesis. I think we should call it the criterion. I think Eigenstate Complexity Criterion, in honor of Marcos Rigol's Eigenstate Thermalization Hypothesis, which this somewhat resembles as a condition. Okay, so that's perhaps the main result. The third useful statement is that the SYK model for large n satisfies this condition, and so its complexity growth matches holographic predictions from the physics of black holes. Interestingly, SYK for n equals 2, which is not chaotic, does not satisfy this condition. So that's an instructive comparison to make as to what happens in those two cases. So this is the body of results, and I'm about to start explaining in more technical terms how this comes about. So it's a good moment for me to pause and take questions. Any questions?
I have a quick question. So these k-local operators, there's no imposition of spatial locality in this system, right? So for example, your two operators are equally simple regardless of whether they couple nearest neighbors or say two spins on the opposite ends of the universe.
The way we've defined it, that's correct, though we've only done this with the SYK model in detail. So, which means that, in that case, there's no notion of spatial locality anyway. I think it's an excellent thing to do to instead imagine a chain, a spin chain or something like that, and include in the definition of locality, proximity. K-local should mean K spins which are contiguous, something like that. That's certainly possible to include and wouldn't change in its essence the details of the analysis. Many of the things would go through in a similar way, but some things may change, and it'd be interesting to understand that. It's certainly going to be necessary to include that kind of criterion when thinking about actual quantum field theories that are extended in space.
I have a question here in Potsdam. One of the, in the considerations of free quantum mechanical systems, in particular free quantum field theories on the lattice, the geometry of unitaries was taken to be such that non-local directions in the sense of spatial locality were not penalized. So my question is, in these simplest example of integrable theories, if you penalize non-local directions, do you also expect to get the linear growth of complexity in time, but perhaps over a shorter time period, or you don't have a clear expectation?
So first of all, at least in our hands, the linear growth, the linear geodesic is always the shortest ones for short periods of time.
Always, regardless of chaoticity or this.
Right. But what happens, we will see a specific example of that. SYK for n equals 2 is integrable, right? Anyway, it's solvable completely. So you'll see there that exactly what happens is you get the linear geodesic stops being, the initial linear geodesic stops being the minimizing geodesic very quickly. Mm-hmm. And so things change. So I would imagine that something similar to that would happen.
I see.
And it's interesting. So I think there's a whole mine of interesting things to be done there. I mean, so on the one hand, we're talking here about, we'll put a metric shortly in which the complex directions are heavy or cost you a lot, so the geodesic sort of sticks to the light directions, so to speak. But I think it's very interesting to understand the trajectories of these geodesics and how they interfere with each other, which one is minimizing when, and so on and so forth. And because the fact that this notion of complexity is related to these kinds of spectral or eigenstate properties means, I think, that there will be a lot of information in these objects about both about integrable and about chaotic theories, and we'll learn something about how these states change with time. So I think there's some interesting things to be done there, even for integrable systems, to be honest.
Yeah, agreed. Thanks.
Yep. Any more questions?
One quick question. So, does this mean that the SYK with two local interactions does not satisfy this eigenstate complexity hypothesis?
That's when I meant by SYK with n equals 2, I didn't mean two local interactions. I meant SYK with n equals 2, the number of spins.
Ah, okay.
So that indeed doesn't satisfy this hypothesis.
Okay.
Yeah. Okay.
Do you have a question, Lars?
Yeah. So question, since you mentioned a few times here real quantum field theories, those have infinite, the number of dimensions is infinite there. So do you have ideas as to how to approach? Will you get anything useful from, will you have something useful to say about those as well?
So depends on the definition of useful. But so we haven't, first of all, let me just stipulate, we haven't studied quantum field theories because, directly here. So there will I guarantee that there will be new subtleties that will arise when one studies continuing quantum field theories. But certainly what I had in mind is to imagine putting the field theory, define the field theory in terms of the continuum limit of the lattice. And then for every lattice theory, you can definitely do this kind of thing. And then there will be some part of the definition of the continuum quantum field theory that descends from the lattice for which all of these considerations hold. I think the whole process of changing these things, it's an infinite dimensional Hilbert space at that time. And, the SU n/2 is SU infinity. So understanding those limits carefully is clearly going to be interesting. There will be issues with divergences that will have to be properly taken care of, things of this nature. So, I'm stating the obvious, I think. We could go into more detail as to what that would take at the end, if you don't mind. And I think that's a very interesting thing to do. That's something I would love to do, actually. But I don't have a more substantive comment on that.
Fair enough.
Did that answer your question or not?
Well, I think.
Yeah, possibly you had something particular in mind about the continuum limit.
Yeah, we can take that later.
Okay. Okay. In that case, perhaps this is a good time for me to continue to discuss the actual technicalities. Okay. So once again, the key statement that, to repeat it, is that if we would like to argue that if a theory satisfies this condition, which we call the eigenstate, the ECH condition, namely, you take all the energy eigenstates, you put the simple operators into the numerator here, and all the operators down here. So this is basically measuring how easy it is to go between one energy eigenstate and another energy eigenstate using the simple operations. This should be exponentially suppressed. So suppose you have this condition, then the claim is that linear complexity growth persists for exponentially long time as expected for black holes. Okay, great. So now let me discuss how we arrive at this and argue that it's all completely practical. So really, this is really a question of studying the geodesics of the unitary group. So SU 2 to the power n/2. So our sort of mental example, the thing that we'll kind of keep in mind is the SYK model with n Majoranas. And the Hamiltonian for such a thing is, we're going to take the Hamiltonian for such a model to involve the product of all possible combinations of Q fermions here, and with some coefficients ji1 to jiq. And as you know, these coefficients are supposed to be drawn randomly from a Gaussian with some variance that's set by n, which is the number of Majoranas, and q, which is the, it's the q locality, if you like, of this interaction. Right? There are, of course, many variants of this model that have been discussed, and we expect that many of the considerations will persist for some of those variants, but we haven't studied that in any detail. And going back to the question somebody asked about spatial locality, of course there are variants of the SYK which involve chains of SYK and SYKs in different sites, and there you could ask the question about how local you need to be across sites in these interactions. Okay, so here we have the unitary group. We're going to take it to be SU2 to the n over 2 for these many Majorana fermions, and we are dropping the overall phase, as I said before. Okay, so we need a basis for the generators. So we're going to take them to be the gamma matrices. So here A runs between 0 and n minus 1. The gamma matrices satisfy the usual algebra, anti-commute to 2 times delta AB. So again, to recall the SYK model, the gammas are basically the fermions psi A. Okay, so from this, I'm going to construct my basis of generators, and here it is. So we'll take products of the gammas. So here are gamma A1 through gamma AM, where m's are, set 1 through n, and some ordering of these coefficients. And you take the products of the gammas, and I'm going to define that to be, I'm going to take that to be a basis for my generators of the group. So here I'm going to use the composite index I to mean, various combinations of the indices of the gamma matrices. So it's possible to show that these Ti form a basis for SU 2 to the n over 2. So the next step, as we recall, so now we've defined a basis, so we know what the tangent space to the group looks like in this language at every point. The next step is to define a metric that satisfies the properties we had earlier. So let me first remind you, the usual way we would talk about a metric on this group is we consider the commutator. The commutator gives us structure constants. So Ti commutator Tj is I times Fijl, TL, that kind of thing. From that, it is standard to construct the Cartan-Killing form. Cartan-Killing form is basically quadratic form in terms of the structure constants divided by the dual Coxeter number. So this is the standard Cartan-Killing form. We are going to take the metric on the group to look like this. We'll take the Cartan-Killing form, and then we'll multiply it by Ci plus Cj over 2. Remember, I and j index the direction in the tangent space, and the Ci are going to be cost factors that will, if you like, reward easy directions and punish, hard directions. So let's set that up.
So you're going to be using L2 norm. Metric.
Yes, exactly. So here we go. So this is going to be my metric. So first, let me tell you about the cost factors. So if I is a k local direction, so less than k gamma matrices, and if you're using a q local SYK, probably you want k to be equal to q. Then let's say that we take we'll take that the cost factor in those k local directions to be equal to 1. And then for all the other I, so which are more complex, if you like, more complex directions, we'll set Ci to equal 1 plus mu, where mu is exponential in S and epsilon is some arbitrary coefficient. Okay, so in this, once you've set this metric up, suppose you have tangents at u, x, and y, then what you do is, and you want to compute, a distance. You want to write down what is the metric on that tangent space. The way you define the metric on the tangent space at any point is you have x and y to be tangents to you. You pull back the x and y, with the operator u inverse. You just bring them back to the identity, if you like, and then you compute the metric g there. Right. So this is the definition that we're going to take of the metric on SU2 to the n over 2. So the geodesic equation, so then the next step is to clearly write down the geodesic equation SU2 to the n over 2. And each one of these steps is pretty pedestrian. I'm just emphasizing that this is completely practical. It's not, thinking about complexity in quantum field theory feels like this kind of weird, mysterious thing. But this is all completely practical, right? We're just doing standard differential geometry and just grinding out the answer. So with a little bit of work, you can show that the geodesic equation on the group manifold then looks like this. Remember, V here are, let me take you back to this. V, where did I define the operators V? Maybe I didn't. I think I did. Yeah. So I'm defining operators in this way. O is equal to Vi, Ti. So Vi are the coefficients of the tangent vectors. So in that language, we have here that Gij dV ds is equal to structure constants times the it's some quadratic thing in the V's with the G with the metric put in again. So this is something called the Euler. I've written Arnold, but that should be Arnold. The Euler-Arnold equation. And this geodesic equation is using the standard Levi-Civita torsionless connection on the manifold. Right. Great, fine. So Vi of S. So S is the parameter of the geodesic, and Vi of S are tangents to the paths. So in this, so once you've solved this equation, U of S, which is the operator that comes about from some trajectory, is the is the path ordered exponential of the integral of the tangents times V. Right. So that's all standard, and we need to set up a boundary condition for this geodesic equation because we want to start at the identity, and we want to end at e to the minus iht. So at time t, this is our target unitary that we want to get to, and then we're supposed to evaluate the Euler-Arnold equation to find all the geodesics, and the complexity of the target time evolution operator is going to be the minimum over all the geodesics of the length of the path. Great. So it's all completely defined. So let's work out first an example for SU2. So this is the SYK with 2 fermions. This is the example we were talking about earlier as not showing the kind of growth that we'd expect in a chaotic system, which is good. So here, just to be practical, we have 3 generators, T1, T2, and T3 for SU2, and we're going to take them to be the gamma 1, gamma 2, and the product I, gamma 2, 1, gamma 2, and I'm going to take this to be the hard direction, right? This T3 to be the hard direction. Okay, so, that's my, I think that's my email beeping. I wish there was a way of shutting it off. I'd have to shut down the screen. I think I'm just going to keep going. If it gets too annoying, I'll do something about it. But right. So the Cartan-Killing form here is simply the identity. So the metric that we're going to put is Gij is the identity, except that it's diagonal, but the last the 3 component is 1 plus mu. Remember, mu is exponential in the entropy. Once again, we're going to consider all operators to be a sum of Vi, Ti, where Ti are the generators, and the Euler-Arnold equation, in this case, is super simple. We get 3 equations. Here's one, dV1 ds is equal to minus 2 mu V2 V3, and so on and so forth. So we can write down 3 equations of this form. So we can solve it. And if you squint at this for a little while, it's easy enough to see that this coupled system of differential equations is solved by taking some coefficients, V1, V2, V3, some sines and cosines in terms of the parameter of the geodesic, and that's it. Right? And then the third one here, the third direction is constant. This is going to be the complex direction, so that you're not moving in that direction. Okay. So now the complexity is the length.
Sorry, a quick question. So is it direct for general mu, or like this is a solution for mu going to infinity?
So this is derived for general mu.
Okay.
In this case, yeah. So, so you can write down the length, and it's this thing, and great. And then you can also find what the operator is that you're at, and this is the same formula we had earlier. A Hamiltonian is some sum of the generators. So let's draw a picture of what you get out of this. So if you write out the complexity for fixed J1, J2, and J3, let me remind you what J1, J2, and J3 are. Let's go back to the SYK Hamiltonian here. Where is it? Maybe I didn't have it. Over here. In the SYK, there are these coefficients that multiply all the fermions. So the J1, J2, and J3 are those coefficients. So in terms of those coefficients, if you fix those coefficients, basically the couplings of the SYK model, and you evaluate the complexity, it does this. It goes up, down, up, down, up, down. It's certainly not growing linearly for a long time. And the reason for this is that SU2 is, of course, a sphere. So suppose you go from here to here for a while. At some point, the shorter path is in the other direction. So some other geodesic takes over. And then they sort of exchange roles and keep going like this. So the net result is that the complexity of the thing, as defined here, oscillates in this manner. That's interesting. And so it's certainly not growing linearly for an exponentially long time. And but one interesting thing happens that, really in the SYK, you're supposed to pick these couplings J1, J2, and J3 kind of randomly from an ensemble and then average. So if you do that, if you ensemble average over many J, then depending on what J's you pick, you get bigger slopes and smaller slopes and, and so on and so forth. So the net effect for these oscillations, and the net effect is that if you average them, initially there's a ramp because everybody's ramping up, but eventually there's a dephasing because, these things all have different periods, if you like, for the oscillation. So they dephase and they average out. So you can show analytically that there's a sort of ramp followed by a plateau. You may recall that one of the things that's interesting that people like to talk about in SYK models is there's this dip ramp plateau kind of phenomenon. So here we're seeing a ramping of the complexity, if you like, and then a plateau, which is coming from competition between different geodesics. I think that's kind of interesting. I'm not entirely sure what to make of it or what use to play to make of it, but it's still interesting that the averaging over random couplings plays a role similar to what we later see happens because of chaos in the fully fledged system. Yes, there was a question.
I just want to make a quick comment,
Yes.
which is somewhat related to what you said, but not the physics is a bit different. So in this works in free theories where one is able to actually vigorously demonstrate what is the shortest geodesic and so on and so forth. The answer for the complexity of the free system is a sum over various momentum modes. And these different momentum modes exhibit oscillations, so maybe not zigzags like you drew, but like genuine sine, cosine oscillations. But then, because the total complexity is a sum of these two, we see a very similar structure to what you get after averaging over this order, which is like a growth or actually a decay, and then eventually a very quick saturation.
Thanks a lot for that comment. And as you say, this is the two statements are clearly in excellent analogy. So in both, so maybe going back to the comment you made earlier about looking at free theories, maybe this is a general thing that integrable theories, if the theory is exactly integrable, then probably there's going to be oscillations, things like that. But once you add some disorder, there could be dephasing of this kind with this kind of phenomenon, like these things kind of settle down in some way. Maybe that's a general thing that can be said about the structure of all such theories. That would be interesting to do in general for integrable theories or something. So thank you very much for that comment. May I continue?
Sure, thanks.
Let me interject a 15-minute timing announcement at this point, just for your planning purposes.
Sure. I think I'm getting, I think this will work well. I think I'll finish on time. Okay, so the interesting thing for us is to look at general N. And general N means, well, you got to look at the Lie algebra of SUN over 2. That's a bit complicated. We are going to take still a basis to be the product of the gamma matrices. And okay, so it's not really necessary for us to go through all the details, but there's some just to emphasize that this is completely a practical exercise. If you look at the structure constants and the ones that are zero and non-zero can be classified in terms of which ones are how the indices work relative to each other, bitwise ORs, bitwise ANDs, and so on. So there's some algebra of these things, which let's not go into detail in view of the time. And so I'm not going to talk about the details of exactly what the structure constants are. In any case, at the end of the day, it's still the case that the Cartan-Killing form is diagonal. And we're going to take alpha to be easy directions and alpha dot to be hard directions. So if you do that, the structure of the Euler-Arnold equation is given here. Right. So once again, we're defining the metric in terms of it's 1 in the easy directions and e to the epsilon s in the hard directions times the Cartan-Killing form. So it turns out that if you do this, then you get the following form for the Euler-Arnold equation. So you get dVds involves some matrix here, which has local, if you like, indices in this matrix, and here are non-local indices. But then the local indices somehow act on this thing in the non-local direction. Anyway, I think we don't have time to go through the details of exactly how this is solved, but the equation is very structured. It doesn't, and you can use the structure constants powerfully to make some progress on trying to solve this. And so I'm not going to discuss in detail how we solved it. The details are there in the paper, of course. So you can try to start working out solutions to this equation. And it turns out that one solution is simply the obvious one, which is you just simply flow in the easy directions at constant speed. And you don't flow in the hard directions at all. So there are geodesics of this form. So, which is not surprising, you're just flowing in a straight line along the easy directions. So in that case, the unitary operator that you would get is e to the I v alpha t alpha s, where t alpha were the generators and v alpha is the initial velocity you give in that direction. So this is the the obvious solution that you're going to get out of these equations. So suppose the Hamiltonian is k-local, and our goal is going to be to show that this is the only solution or this is the shortest geodesic for a very long time, right? That's what we have to show, right? But first, let me just emphasize that if the Hamiltonian is k-local, so H is J alpha T alpha, where alpha are the local directions, if you like, then the target you want to reach is e to the I v alpha T alpha s. That's e to the I h s, if you like. And so if you take v alpha equals j alpha t, so you take the initial velocity, these coefficients, the Hamiltonian times time, then you'll reach there. And if this is the shortest geodesic, then the complexity is time times something involving all of these coefficients in the Hamiltonian. So this would match holographic expectations. So our goal now is to show that this is the shortest geodesic. So what are the obstructions to this being the shortest geodesic? Well, there are two kinds of things that could happen. One is you could have complicated geodesic loops, and for for a group with a complicated global structure like SU n over 2, this is an issue that needs to be addressed. We have not fully addressed it. We had some ideas about what to do, which we could perhaps talk about later, but that's something that we will not address in this talk, although we've had some progress that we haven't reported on. The other kind of threat is something called a conjugate point. And a conjugate point is a thing like this. So, so suppose you have a geodesic that goes between here and here. It could have, this is the linear geodesic. Suppose you perturb at first order this geodesic. So you go a little bit into the complex direction. It could be that the thing goes a little bit in the complex direction and then zips back and hits this over here, and that's actually a shortcut. That could easily happen, right? And indeed for SU2, that is what happens. You get lots of conjugate points of these kinds, right? You could perturb the initial geodesic by a small amount, and will come back eventually and take over, even though it was a small perturbation. So it's not an empty problem. This thing can happen. So this is what we're going to address, the absence of conjugate points for an exponentially long time. So how do you find the conjugate points? Let me check the time. Yes, we're in good time. So here's the unperturbed linear geodesic. You have the initial velocity being Hamiltonian times time. And what we're going to do is we're going to take this initial velocity and perturb it. We're going to take h of t plus some delta v. And we want to ask, can you intersect back into the trajectory? So there's a first order perturbation of the geodesic equation, of the Euler-Arnold equation, called the Jacobi equation. And it has the following form. This is just a matter of grinding things out, mechanically. It involves the generators, involves the perturbations, involves the kind of things you'd expect it to, and has this form. This form. So if you take delta VL to be expanded in terms of, so let delta V be the perturbation. Let's project the perturbation partly onto the local directions and partly onto the non-local directions. I should have said that. Then the Jacobi equation, namely the first order perturbation of the geodesic equation, takes the form given here with some commutators and so on. So you basically have to solve this to see does it have a solution. So that's complicated. and takes a little work. So I'm going to try to give you the answer and then extract the physics from it. So we want this kind of picture. Here's the linear geodesic, and we're looking for a solution where a small perturbation leads to a geodesic that lands over there. So
the perturbation is only in cheap directions or also in hard directions?
Both. It's in so here it has a projection onto the easy directions, that's delta VL, and has a projection onto the hard directions.
Yeah, thanks.
So so a conjugate point occurs. So you have U of 1, which is the final operator you're supposed to come to, and this is now going to be e to the minus IHT minus I delta U of 1. That's because you've perturbed the initial trajectory. But what you want is, if I multiply this by U inverse, then I want U inverse times delta U1 to be 0. Namely, I want to arrive back at a point on the trajectory. Okay. So it takes a bit of massaging to get to this, but you can show that the initial perturbation is mapped to some U inverse, into some final perturbation of the location arrive by the following kind, by this super operator. So you have this delta V naught, the initial perturbation. And if I want to find out the final thing, I can apply this Y mu, this super operator, to this operator delta V naught, and that will give me the answer. So that you get this complicated expression. So notice that there's the perturbation in it. There's various exponentials of, parameters of the geodesic and time and commutators of the Hamiltonian with the generators. So this is not a straightforward looking expression, but you can simplify this expression considerably by working in a basis of energy eigenstates. That's because there's the Hamiltonian floating around many places, and you can make this look much simpler if you just agree that you're going to expand everything in a basis of energy eigenstates. And where is that? Okay. All right. So here's the way we're going to think about this. So you have this complicated operator Y, and conjugate points are basically zero modes of Y. Why is that? So there's zero modes of Y because if Y acts on delta V naught to give you a 0, then it's mapping this to 0, and so you're looking for zero modes of the super operator Y. So there are two. Okay, so let's think about two kinds of situations. So one is where all directions are easy. So in that case, if you expand in a basis of energy eigenstates, here's what you find. You find that Y, the super operator, is some phases involving the energies times the eigenstate M and N. You can check that this is the case in that situation. And so then you'll find that these phases out front are various exponentials of the energy gaps divided by the energy gaps. So that's what turns out to be the case. And then if you want this, what you want is this overall thing appearing in front. It's not just a phase, I guess. It's this number appearing in front. You want it to be 0. And you can work out that this thing will be 0 if at some critical time 2 pi divided by the maximum energy minus the minimum energy in the system. So that's basically because you can see that if you look at the e to the I delta mn times t, if you pick t to be like this tc, then this thing will be equal to 0. So that's the earliest time at which you'll get a 0. So now you see that if all the directions are easy, then you're going to find that you will get a conjugate point when at this time, and in the SYK model, delta max, the difference between the maximum and minimum energies is like order n. So you will get a critical time pretty quickly, right? You'll get a conjugate point within a time 2 pi over n, which is very quick. Okay, so this shows that if all the directions are easy, conjugate points occur quickly. So you won't get linear growth and complexity for a very long time. Okay, so that's to show that this is not an empty problem. Now we agree that only k local directions are easy. And then I'm going to assume this ECH criterion we talked about earlier, saying that energy eigenstates cannot be mapped to other energy eigenstates by the simple or k local operators. So applying this condition, you can again go to that super operator that maps initial perturbations into final perturbations and grind through again. This again takes a certain amount of algebra. And if you keep grinding through for a while, you'll find, you can write things in terms of the spectrum of the theory and so on, and you'll get some expression, again, involving some coefficients phi mn times the energy eigenstates. And in view of the time, I'm just going to keep going without talking through the details of these expressions. You find by a similar set of arguments to what we said earlier, that the critical time at which you will get a conjugate point goes like 2 pi divided by the maximum energy gap, the maximum, the minimum, but now multiplied by 1 plus e to the epsilon s, where s is exponential in the entropy. Okay, so here, again, remember that this delta max, the maximum energy gap in the SYK model, goes like order n. And I haven't put in the correction terms here, but those can be bounded by e to the minus entropy times polynomial in the entropy. That's because that's the way we set up this this criterion in this ECH criterion. About this was the error term, the overlap between the energy eigenstates when acted upon by the easy operators. So I could go through the details of this algebra, but actually I think it's better for me. But this is the last technical slide I have. So I think rather than going through this algebra, I'd like to make a couple of qualitative points instead. I'm almost out of time here. So the first thing is that we have to ask, does SYK satisfy this ECH criterion? So we did not prove that analytically. We took n of different sizes and sort of numerically checked that this ECH criterion is satisfied by the SYK model for larger n. So that means that indeed in the SYK model, the linear geodesic by these arguments is the shortest one for a time exponential in the entropy. So that's kind of what we wanted to show. So that's the first comment I wanted to make. So the second comment goes back to the various questions that were raised earlier. What would be nice to do next? So there are many things that would be nice to do. One is to understand clearly the difference between integrable theories and chaotic theories. So this is a chaotic theory, presumably SYK at large n that we're talking about. And so following the remarks that were made earlier, indeed, it's possible that integrable theories in general show these phenomena where there are oscillations in the complexity followed by averaging giving rise to a plateau. That would be interesting to understand, establish as a general statement for integrable theories. It's possible. Then we can talk about chaotic theories. Now, chaotic theories, there can be different degrees of chaos, right? There can be maximal chaos, less chaos. It's possible that the complexity of time evolution could serve as a kind of order parameter for separating theories that have different degrees of chaos, right? So I'm sort of used to thinking, at least traditionally, about whoops, what just happened? I'm used to thinking traditionally about Lyapunov exponents, and presumably the Lyapunov growth is sharper, it's somehow more chaotic, less chaotic. I think it'd be interesting to understand if there are sort of universality classes of theories that have a certain amount of, where the complexity growth separates different degrees of chaos. Right, so that would be, I think, an interesting thing to understand. I have no clear reason to suggest that that would happen, but it seems reasonable that something like that might happen. Some things, clearly such a thing as maximal chaos. Are there discrete classes of chaotic theories? Are they, or is there a continuum of chaotic theories? I don't know, but it would be interesting to understand. And if we have some sort of agreed upon actual technical definition of what complexity is, we could apply that. The third kind of comment I'd like to make is that clearly I did this with discrete spin systems and so on here. I think it's an important problem to try to extend this kind of reasoning, if possible, to continuum theories. One should anticipate the usual difficulties arising with things being somewhat ill-defined in the continuum and needing regulation, and then the definitions would need to be modified appropriately to deal with that. You can hide an infinite amount of complexity in, the decimal expansions of real numbers. So one has to pay attention to that as to exactly what one wants to mean. But that's an interesting problem to solve, and I think we can probably make some progress on that. I'll stop here because I think this is it on time.
Thanks a lot, Vijay. Questions?
I have a question. Actually.
Yeah.
So in your expression for complexity, when you say that it's like T times sum of J alpha, so you know how that's scale with N and K?
You mean this expression?
Yes, this one. Yeah.
So how it scales with N and K. Let's see. So alpha here is a sum over all of the coefficients, right? So the number of coefficients counts the number of operators that you may have in the Hamiltonian. So if you include all k local operators out of n operators, so suppose you had n fermions and you're using k of them, then you have n choose k. So you'd have n choose k of these things. So you'd have square root of n choose k.
I see. Okay, thank you.
Yeah. Again, all else being equal about the coefficients, of course.
So I have a question here in Potsdam. So one lesson that I took from your talk and more broadly from this work is that even if you have a chaotic system and you take a definition of complexity, does not penalize directions that do not appear in the Hamiltonian, then you do not get the linear growth. You get very quickly something else.
So that would indeed be perhaps the lesson of this. Where is that slide? This slide.
Mm-hmm.
Right. I think that's correct. That's interesting. I mean, this has some relationship to the idea in computer science that the complexity of a problem depends upon what you choose to be the gate set.
No, of course. No, I agree with this. I mean, I was saying this because, like part of the reasons that is why we here in Potsdam were playing with these ideas was to try to maybe do not address directly at the moment the holographic problem, but try to see what do we learn indirectly about the holographic problem, assuming that holographic complexity proposals are about complexity, right? And
yes.
From these observations, it seems that, well, if holographic complexity proposals are about complexity, maybe they better use the cost function, the metric that penalizes non-local directions on the boundary, so to speak, right?
So I think that's I do think that's correct. And that's going to be necessary to match up with the holographic complexity proposal. By the way, I've appreciated your papers, so and learned from them. To connect up with the holographic problem, if one is not doing SYK ADS2, then I think one will also need to address the issue of spatial locality, which we have not addressed in this work. I think that's going to be important for that.
No, I'm saying that actually it's a bit, I mean, it's better in a sense that, well, in our latest paper on the topic, we look at 1+1 dimensional CFTs. And over there, we used, stress tensor as stress tensor components at various locations as gates and nothing else. And we derive something that is based on conformal symmetry, so it's fully universal. And what I'm saying is that you can think of enlarging your gate set by including, say, all the primary operators, maybe quasi-primaries, right, in your CFT and a stress tensor. And the good news is that this is the stuff that actually has a natural counterpart in the bulk, which is the supergravity fields, right?
Yes.
And as a result, like you might hope that, well, playing with the sources and doing some sort of Lukowitz-Malacena argument, you might be able to actually derive one of the proposals, or maybe something else, maybe something that is a proper counterpart of complexity for holographic CFTs or QFTs.
Yes, I agree. It's a very good idea to try to do that. And indeed, you know, as you're saying, sort of the natural algebra of local operator. Well, we know what the natural algebra of local operators is in a CFT. As you say, there's the stress tensor, there's the primaries, you know, there are various descendants and so on and so forth. And so we know a lot about those algebras. And so one thing I'm not entirely clear on is how to, how to apply Lefkowitz-Maldacena type reasoning to this setup. So once there is a technical definition of complexity in field theory, in any approximation, right? Free, not free, whatever we have, we'd like a formulation. I mean, and there's a particular formulation we're giving of that here, right? We'd like a formulation that we could indeed turn into. I mean, I've been wondering about this. You know, how to I mean, so the way Lefkowitz-Maldacena worked was to say, well, you know, the basic definition of holography is a relationship between partition functions.
Exactly.
Once there's a relation between partition functions, you've got one partition function, the other one, you've got replica this, replica that, blah, 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 technical problems regarding, you know, singularity of the bulk, but okay, we'll fix them, and then you get an answer. So one virtue, I think, of the definition we've been trying to give here is it relates this notion of complexity to something like the spectrum and, you know, the structure of the eigenstates and things, which are sort of things for which I can imagine trying to build a correspondence. So ideally, we'd like something that sort of directly, for which we already know a relationship, right? So we'd like to say that the complexity can be derived by some operation on an object for which we already have a holographic correspondence. The partition sum was an example of that in Lefkowitz-Maldacena. So if you have that, if you can write the complexity as an operation on a thing for which there's a holographic correspondence, then we could define the bulk operation also and sort of derive the relationship. That's, I think, the ideal thing that we should strive for here. This is in line with what you're saying. As in first we could identify which operators are relevant, this, that, and the other. Then we could identify the object which we have to manipulate in the field theory to get the complexity, and then say what is the analog of that object. We want to start with an object for which the dual is known, and then do the manipulation of some kind.
Exactly. Completely agree.
Yeah. No, it would be really great to make progress with that. And like you, I agree that the key step is understanding how to do these things in the field theory.
Can I have maybe one final short question? Otherwise, you can also bug Vijay off the record, as it were. Okay, so if not, let's thank the speaker again.
Yeah.